So the first thing I want to show you, and again, this is 4.6, we're only going to get into graphs of tangent functions. So if you're curious about the other three, the honor students will be doing secant and cosecant functions, which is basically a sine and cosine, or sine and cosine function. Nobody will be graphing cotangent functions because they're essentially a tangent function in the opposite direction. But we will only be going through sine, cosine, tangent. So what a tangent function even looks like, right? We talk about like basics first. This one looks a little bit different. So in this case, when I have my dashed lines, they're actually representing asymptotes. It's not just my like makeshift of meeting. And let me grab my thing. See. So we have these dashed lines for our asymptotes. You can already start to see some differences between the tangent function and a sine or cosine. Okay, so now we have to label this axis. So what happens is we end up getting the same kind of pattern, because just like a sine or cosine function, tangent functions are continuous. Like they will go left and right forever, except for the fact that they're going to have asymptotes to keep them kind of in line. So they look like this funny little curve in between these asymptotes. They cross over about center way through. And the first one always starts on that origin. We're not going to get into any of the horizontal functions. We're just going to kind of stay with the basics with them. So that first one, again, is always going to cross through the origin, meaning that our asymptotes are on the left and right side of that. So our first asymptotes are at negative pi over 2 and at positive pi over 2. And then thereafter, they just keep kind of going on every pi over 2 interval. So then it will be 3 pi over 2. And why not draw one more? 5 pi over 2. Okay. So again, interval of pi over 2. So we look at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, and so on. That means that where this tangent function crosses my x-axis is always going to be at a whole pi. So at pi, 2 pi, 3 pi, and so on. So this is negative pi. So let's talk about a couple of the differences. So already, one, we have an asymptote all over the place. Sine functions and cosine functions don't have those. The curve looks a lot different. The period is also different. If we are going from negative pi over 2 to pi over 2, pi over 2 to 3 pi over 2, this period is always, I don't know where I have room on here. Period is always pi length. Okay, so this new period is pi, which is different from our original cosine and sine. Those are usually 2 pi. So the two main things that we're going to deal with is having an a value and a b value. We're not even really going to use the c value for tangent functions, because all of that, truthfully, you know how to kind of divide up your intervals with your cosine functions. With a tangent, it's even easier. So if you can do those with a sine or cosine function, if you had with a tangent, you'd always be able to. And tangent's not going to be your most common function either. So to find our asymptotes, it's a lot like how you found your left and right endpoints. So we take that bx minus c and we set it equal to negative pi over 2. So that one's a lot different than the left endpoint, right? Left endpoint was always set equal to 0 because a sine or cosine function started at 0. Now we're talking about our beginning two asymptotes. So that first asymptote is negative pi over 2. The second one is positive pi over 2. So to find your second asymptote, you set it equal to positive pi over 2. Okay, so another small little difference there. Your a value, so again, your tangent function would be y equals a tangent bx minus c. So your a value essentially changes the curve of the tangent. So for example, if your a equals something like 1 to 4, it's going to come up and take like a really sharp curve. That's probably over-exaggerative, but it takes a sharper curve. If you had an a of a larger whole number, such as 5, this is a very gradual curve instead, where it has more of a straight line. Here, when it's 1, it's just kind of, it curves, but it's nothing too fancy. Okay, hey Mike. And the last thing we're going to kind of talk about with this is what if we have a negative a value? So a negative a with a sine cosine function flips it, right? So a normal sine function starts up, comes down, goes up. Normal cosine function starts up, goes down, comes up. And their reflection is just the exact opposite way, right? So that's cosine sine. When we're talking about tangent, the only way you can flip it is to reflect it back the other way. So if you have, and I'm running out of room on here, if you have a negative a, you're going to go the opposite direction, okay? So instead of going up to the right, you will come down to the right. And that's the one and only difference. One and only difference. I'll give you guys a minute to write all that. It's a lot like quicker and easier than anything we dealt with before. We're just going to do a couple of examples today. I truthfully only have 2 for you to do. I don't think you need any more than that for the function. They're a lot more straightforward and a lot less going on with them. Okay, so let's start by graphing y equals, let's do 1/6 tangent x over 2. 1/6 tangent x over 2. So just like we did before, we want to pull out our b value. When we did sine for the first time with the b value, we had that fraction where it said x over 2. Again, your book, like if you go into calculus, this is more how you're going to see it written. I like to pull this apart so that we can see the b value separate. So that would be 1/6 tangent 1/2 x, right? Just literally pulling out that b value so it's more obvious to me. Because 1/2 x is the same thing as x. So this allows me to see that my a value is 1/6 because a is always what's directly in front. What's nice is the way that these are written are not changed from a value will always be in the same place for all 6 of them. So a is always directly attached to that trig function. B is always directly in front of the x. So my b value is 1/2. And we're not talking about c values. We need them for our asymptote. So for that fact, it's going to be 0 since there's nothing in parentheses added on here. So we want to first start out by finding these asymptotes. Okay, I don't even know where to start with my graph if I don't know where my asymptote is going to be. So we have bx minus c equals negative pi over 2. That means I have to take my bx minus c, which here is just 1/2 x. instead of equal to negative pi over 2. Oh, I forgot my x. As always, we just need to solve for x in order to find out that asymptote. So solving for x, I'm going to multiply by positive 2. Okay, to get rid of a fraction, I need to multiply by that denominator. So multiplying both sides by 2 cancels this out to give me x. On this side, negative pi over 2 times 2. Again, 2's are going to cancel to give me negative pi. And for my other asymptote, bx minus c equals positive pi over 2. The other nice thing about these is they're pretty much going to be the negative and positive number of each other. So since this one was a negative pi, this one should be a positive pi. We multiply both sides by 2 to again get x equals then positive pi. So what does this mean for our graph? Let's start making that out. For our graph, all of our asymptotes will go in intervals of pi. So if the first one's over here at negative pi, second one's over here at positive pi. I always will want you, especially for tangent, at least 2 periods of this. So I have to figure out then, well, where's my next asymptote going to be at? Between negative pi and positive pi, 2 pi happens, right? There's 1 and then 2, meaning that a full period for this function is 2 pi. Remember, a b value changes your period length, so it's not a surprise that it's not pi for this one. So where does that mean my next asymptote will be at then? Over here. We have to have 2 pi in between each of them. I add another 2 to get 3 pi. Okay. And the middle of that would be 2 pi then, right? Middle of pi and 3 pi would be 2 pi. So I have my 2 periods here that I can draw. And now I just want to count in my a value. Remember, we said fractions create a greater curve when I cross through my middle. A whole number creates a much softer curve. So just show me that you know, like, yeah, there should be some kind of hard curve going through there. Some kind of hard curve crossing through the middle. 1/6 is a pretty small fraction, so it's a pretty dominant curve. And that's it, right? B value, find your asymptotes, figure out where the next one's going to be, account for your A value, and draw your curve. Do you have any questions? Do you guys like this one better than sine, cosine? You don't? I do. I don't know why, I just think they're so much easier for some people. Okay, I'm not going to erase this one yet, but I am going to give you one for you guys to try. I'm going to leave this one up here, so if you need to keep looking back at it or still write down some stuff, you can. The next and last one I want you to try is to sketch y equals -4 tangent to x. -4 tangent to x. Oh yeah, we got it. One at a time to try this on your own. Yes, first we do still attend white side on Monday. I got to that. Okay, so let's go through this one really quick. All right, so let's identify a couple of things first. That first one, we always take an absolute value of our A value. So in this case, it's going to be 4, right? But we want to account for the fact that A is negative. So when we have a negative A, it no longer goes up and over. It's instead going to go down and over, right? So that curve just quite literally flips. Our B value, I don't know why I wrote an arrow there. B value is 2. So because we have a B value and that's not 1, we do have to find where these new asymptotes are going to be. So we're going to take bx minus c, again, equals pi over 2. So in this case, 2x equals negative pi over 2. We're going to divide by 2. So this is one that some people have trouble with because we're dividing a fraction by a whole number. So I was telling everyone, you always can multiply by a reciprocal. If you're dividing by a number, you are always welcome to multiply by a reciprocal instead. So the reciprocal of 2, right, since 2 is technically 2 over 1, the reciprocal of 2 would be 1/2, giving us a negative pi over 4 as that first asymptote. Okay, super similarly, bx minus c equals pi over 2. So 2x equals pi over 2. X in that same circumstance, because we're dividing by 2, multiplying by its reciprocal, right? This is the same process for both of these, will be pi over 4. So let's go draw out where these asymptotes will be. We have negative pi over 4 and positive pi over 4. Okay, and we can do one more period, but I want to get you through this one, make sure you have it correctly. Because it's a 4 for our A value, that's a softer curve, right? It's not quite as prominent as this. It's more straighter the higher the number. And because it's a negative, it's got to go backwards. So I just try to draw this like, as long as you put some effort into it, I'm okay with it because I'm also not fantastic at drawing these. That would be how you could do that, right? And if you wanted to go ahead and label out the rest of these, you can count up just like you would with a sine function. So pi over 2 or pi over 4, 2 pi over 4, 3 pi over 4, and so on. You could have one more super not prominent curve right there. Type field or tangent function. Sweet. Thank you. We'll practice more of these tomorrow. Okay? I think you're going to have a lot